Why are astronomers so anxious about the new discoveries from the James Webb telescope? Because for nearly a century, scientists have been trying to answer what exactly the Hubble constant is. This seemingly simple number actually determines the rate of expansion of the universe, and the accuracy of this number. It is not just about whether we can accurately measure the size of the universe, but also about how we predict the future evolution of the universe. However, recent data from the Webb telescope has completely overturned our understanding of this number. This is not just a scientific issue, but a major challenge to our entire view of the universe. All of these questions. Everything must begin with a re-examination of the Hubble constant. The Hubble constant was first proposed about 100 years ago. At that time, astronomer Edwin Hubble, based on his own observations, provided a preliminary estimate, 500 kilometers per second per megaparsec. This meant that the universe was expanding at an extremely fast rate, almost beyond our imagination. Imagine this. It is like when you are decorating a cake and happily spraying whipped cream, but suddenly you see that layer of cream instantly covering an entire city. Such an astonishing expansion rate made scientists start to doubt Hubble's conclusion, so they decided to re-examine and verify the result. To verify Hubble's estimates, astronomers turned to the cosmic microwave background radiation. The residual radiation formed about 400,000 years after the Big Bang. This microwave background radiation shows regions of lower temperature, and these regions are precisely where the first stars and galaxies formed under gravity, gradually forming regions. By comparing these images of the microwave background radiation, the images of space we observe today, astronomers concluded that the speed of the universe's expansion is much slower than Hubble had estimated. The results show Hubble constant should be 67 kilometers per second per megaparsec, which is 1/7 of Hubble's original estimate. This means the whipped cream would only fill the kitchen, instead of the entire city. However, scientists did not breathe a sigh of relief because of this. On the contrary, they decided to verify this result using another method. This time, the scientists measured the galaxies moving away from us. They used a method known as the standard candle approach. By observing the brightness of certain stars, they could estimate their distance from Earth. These standard candles, these are celestial bodies with known luminosity, such as Cepheid variables and red giants. It is like judging the distance of a car by the brightness of its headlights. Astronomers can compare the actual brightness of these celestial bodies with the brightness we see through telescopes. To calculate their distance from Earth, the deviation is extremely small. Using this method, the calculated value of the Hubble constant is 73 kilometers per second per megaparsec. However, this result differs from previous measurements of the cosmic microwave background by more than 10%. This discrepancy has put scientists in an unprecedented predicament. If the two most reliable verification methods produce different results, it means the fundamental theories of cosmology are facing a crisis. We may have completely misunderstood the evolution of the universe. All the data and research we have accumulated over the years will be overturned. In the face of this situation, scientists have found that admitting the standard candle method is completely wrong is actually more realistic than re-examining Hubble's constant. It is like a mansion that needs to be completely rewired. Troublesome though it may be, but it is still better than tearing it down and rebuilding it. However, the latest data from the Webb telescope has completely shattered all these expectations. Astronomers originally predicted that the most distant galaxies should be very primitive and simple, with almost no special structures. Yet, in the first batch of images taken by the Webb telescope, unexpectedly discovered some strangely shaped, complex ancient galaxies. These galaxies are not only far more advanced than expected, but also, in just 1 year, the number of such galaxies discovered by the Webb telescope is 4 times greater than the total found throughout the entire history of cosmic observation. But the discoveries of the Webb telescope seem far from over. In a distant flame galaxy, the James Webb Space Telescope unexpectedly captured an image of a Cepheid variable star. The previous calculations by the Hubble Space Telescope were correct. Then the moment to reveal the truth has finally arrived. What is shocking is, Webb's new data almost perfectly matches previous observations. This means the Hubble constant calculated using the standard candle method is still valid. So where exactly is the problem? The problem lies in our understanding of the cosmic microwave background radiation. The update to this data is not only a redefinition of the rate at which we know the universe is expanding, but also a profound impact on our theories of cosmic evolution. We have always believed that the universe expands at a relatively stable rate, but this discovery forces us to re-examine everything. Perhaps the real problem does not lie in the scientific theories themselves being wrong, but rather because we have overlooked a crucial fact. The universe is far stranger than we imagined. Its structure goes beyond the framework we currently understand. Can we explain these differences? One possible explanation is the universe is not finite as we understand it. It is infinite. If the universe is infinite, then any attempt to define its size and shape may be doomed to fail. Why can't we simply accept this reality? To accept an infinite universe means we have to face an undeniable fact. This infinite structure could ultimately tear everything we know apart. What exactly makes an infinite universe so dangerous? In 1922, mathematician Alexander Friedman proposed a theoretical model of an infinite universe, but at the time, this hypothesis did not receive much attention. This was because infinity, at that time, was considered a purely mathematical concept. The scientific community found it difficult to regard it as an actual property of the universe. However, Friedman's theory was not without foundation. He laid the foundation for many later breakthroughs in cosmology. To determine whether the universe is finite, scientists decided to measure the curvature of the universe. If the curvature result is 0, it means the universe is infinite. If the result is not 0, then the universe is finite, and it must have a specific shape. However, the results were disappointing. The curvature of the universe is almost 0, with an accuracy of up to 90%. This means the universe we observe is almost an infinite, boundless plane. Why is this dangerous? As the expansion of the universe accelerates, it truly is infinite. Then, the rate of expansion could eventually reach a limit, or even accelerate infinitely. In this scenario, even the original Hubble constant would seem insignificant. The expansion of the universe will accelerate. Eventually, our galaxy will lose contact with all other galaxies and begin to gradually break apart. As time goes on, our solar system will also collapse. In the end, the entire universe will enter a state of complete disintegration. This process is known as the Big Rip model. Scientists predict that when the expansion rate of the universe reaches its limit, all matter will be torn into countless tiny fragments. The universe will become a thin soup of particles. All of this will ultimately lead to the complete collapse of the universe. According to Marcello Visconti's prediction, the Earth will undergo this catastrophic change in about 22 billion years, although this process gives us plenty of time for our future descendants. This disaster could arrive unexpectedly. No matter where they are in the universe, they may not be able to escape this doomsday. No matter which galaxy they are in, they won't be able to avoid this end. However, in recent years, more and more scientists have begun to question the Big Rip and the concept of an infinite universe. With the Planck Space Telescope completing an ultra-detailed full-sky cosmic microwave background map, we have obtained a more accurate measurement of the curvature of the universe. Preliminary data show that the curvature of the universe appears to be close to 0. The margin of error has dropped to 0.4%. That is a reduction from the previous 10%, but this does not mean we can simply accept this result. When astronomers analyzed this result, they raised a new question. If the curvature of the universe falls within this margin of error, this means that in reality, it could be much larger than what we currently observe. Currently observable universe has a diameter of about 93 billion light-years, but data from Planck suggests that the actual size of the universe is at least 250 times larger than the observable part. That may sound hard to believe, but it reminds us of our history. Early humans took a long time to accept the fact that the Earth is a sphere. From the surface of the Earth, the curvature is almost invisible. We need special methods of measurement to reveal the true shape of the universe. According to the latest analysis of Planck data, the curvature of the universe is much smaller than we previously thought. It is almost immeasurable. Its curvature is similar to that of the Earth. This means the universe may not be curved or finite, the way we traditionally understand it. Instead, it is closer to being flat. However, if the universe's curvature is truly this slight, it must have a specific ultimate form, and this form will determine the fate of the universe in the future, depending on the form it takes. Scientists have speculated on several possible futures. Each scenario is more pessimistic than the last. If we take the universe's form literally, it could be fatal. In other words, the structure of the universe determines our future survival. We may face irreversible disasters. To better understand the structure of the universe, we must first figure out the curvature and density of outer space. But this is no easy task. We know the universe is not made up of ordinary matter and energy, but is dominated by dark matter and dark energy. To this day, we still can't precisely measure the distribution, density, or uniformity. This has always been an unsolved mystery in modern science. Imagine this. You are pulling on a piece of cloth, applying force unevenly, and eventually it wrinkles from the stretching. The fate of the universe may also be undergoing similar changes, especially when the density of the universe fluctuates. These fluctuations could lead to structural changes in space itself. If the curvature of the universe is positive and falls within the margin of error measured by Planck, then the universe we live in might not be the flat space we imagine. Instead, it is a massive four-dimensional hypersphere. You can try to imagine it. It is like a huge and complex sphere, but it is different from the three-dimensional spheres we are familiar with. It has four dimensions. Mathematically, the concept of such a hypersphere might seem a bit abstract for our three-dimensional way of thinking, but if you can imagine a geometric form beyond the ordinary, it might not seem so out of reach. Just like the difference between a two-dimensional circle and a three-dimensional sphere, a hypersphere pushes our understanding of space into a new dimension. In 2019, cosmologists at Sapienza University of Rome, Emil Georgi, studied the concept of this hyperspherical universe. If the universe really takes this form, then the likelihood of a Big Rip event would be greatly reduced. However, the problem is far from over. Scientists, we also have to face an even more complex reality, the role of dark matter and dark energy. Scientists believe that in the early moments after the Big Bang, the expansion rate of the universe was driven by these mysterious substances. However, to this day, this expansion is still accelerating at an exponential rate. It continues to speed up. The acceleration of expansion has made the structure of the universe exceptionally smooth, to the point where, with our current technology, we can't precisely measure its curvature. However, the root of the problem may not actually lie in the expansion itself, but rather in the changes of dark matter. In 2017, our astronomer Zhou Gongbo and his team proposed an interesting hypothesis. The properties of dark matter might change over time. You can think of it like a can of Coke in the fridge. At first, the water contracts as the temperature drops, but when ice forms, the force suddenly erupts. Zhou Gongbo believes that dark matter in the universe might become even more rarefied and may eventually stop driving expansion and instead begin to contract space. This theoretical hypothesis is called the Big Crunch. Imagine this. If time were to flow backward, all celestial bodies would contract and eventually return to a single point. But in this process, gravity would become incredibly strong, so much so that stars in the Milky Way would collide violently. Humans might even be slammed against the surface of the Earth. The most extreme scenario might be the simultaneous arrival of the Big Crunch and a new Big Bang. This could potentially destroy everything completely. However, Planck's data makes us reflect once again. The curvature of the universe measured by Planck, an error margin of only 0.4%. But it could be positive. Not just negative, it could also be negative, and within the same margin of error. This means that the universe we observe might have a saddle shape. Unlike a hypersphere, a saddle shape is only a finite part of a four-dimensional structure. From this perspective, what is the true shape of the universe? Once, American writer Howard Bloom proposed a theory, suggesting that the universe might be shaped like a donut. This sounds like something out of a science fiction novel, but just imagine if this theory were scientifically confirmed, how shocked Bloom would be. In fact, theoretical cosmologist James L. from Cambridge University proposed that the universe might actually have a toroidal structure. In this structure, galaxies move like spaceships in old video games. No, in those games, spaceships always disappear off one side of the screen and then reappear on the other side. According to Jean Lee, in this donut-shaped universe, our galaxies not only wander around, but they also move in the same direction, just like in a game. This means we simply can't find the edge of the universe because it is a looping structure. If the curvature of the universe is positive and falls within the margin of error measured by Planck, then our universe might really be a giant hypersphere. So no matter what shape the universe takes, its future is already determined, from the expansion of the universe to its ultimate fate. We are gradually uncovering its mysteries. However, with each new discovery, we also realize that this universe is more complex and more mysterious than we imagined. We are but a fleeting moment in its journey. Yet every step of exploration continually changes our understanding of the universe and of life. What will the universe look like in the future? Perhaps we may never know. But with every scientific breakthrough, we get one step closer to the truth. And that is the meaning behind our relentless pursuit.